All right, this is a continuation of lesson 3 on energy transformation and conservation. So we talked about how there can be a single transformation from one type of energy to another, or multiple transformations, where it's kind of like a domino effect. It just goes from one to another to another to another, until it runs out of observable, kinetic energy and probably just rolls itself up into some kind of a potential energy at that point. One of the most common types of energy transformation is from kinetic energy to some kind of potential energy. And if you remember, we talked about gravitational potential energy and elastic potential energy. So there are two kinds of potential that you want to keep in mind. Here they give you an example of a pendulum. You have been on a pendulum if you have ever rode on like a swing set, um, or maybe tried to hypnotize somebody. So if you imagine this ball in motion, swinging back and forth, its greatest gravitational potential energy is when it's the farthest away from the ground, and then the greatest amount of kinetic energy is at the bottom. We looked at roller coasters and saw that greatest gravitational potential energy is at the top of the hill, greatest kinetic energy is at the bottom. When we did the tennis ball or ball dropping activity, we talked about it's traveling the fastest or has the most kinetic energy right when it hits the ground. So, what you want to do when you're thinking about energy transformations is try to think of what is happening in slow motion. So here they have pictures, probably a high-speed camera took these. Same thing with this pendulum, to try to slow down and look at what is going on at these different points. What kind of energy are we moving from in each step? So here he's running, that's kinetic. A pole vaulter pole is flexible. It has elastic properties, so elastic potential as he bends it. It wants to straighten itself out, which helps propel him up. At this highest point is where the person would have gravitational potential energy. And then as they fall down on the other side, it turns into kinetic. So these can be hard to observe because things move pretty fast sometimes. Um, so if you think of it in kind of a slow motion idea, what's happening? What kinds of energy did I start with? What kinds of energy are going through the middle? And then what do I end up with at the end? The law of conservation of energy we've talked about before. When energy is transformed from one type to another, no energy is lost in the process and no extra energy just shows up from nowhere. So, however much energy you started with at the beginning is how much you need to keep track of throughout the process. So, here we have a roller coaster, and in your book, you're supposed to make these into little bar graphs. So, imagine the PHET site. If this were in motion, what would the bars on the bar graph be doing? How much potential and kinetic would there be at each of these different locations as the roller coaster goes through the ride? And we talked before that however much potential energy the cars have in this first hill, that's how much energy total they have to get through the whole track. So you can't have any more potential or kinetic when you add them together than this amount of potential that you start with initially. One type of energy that is lost or created in the process is thermal energy due to friction. And so it isn't destroyed, but it does kind of take away from the kinetic and the potential. Because it turns itself into thermal and then that doesn't really come back into the system. Most of these examples are kind of thought of without using friction, because keeping track of that can be difficult. So you want to make sure, however long these little bars are in your graph, that they equal out to 100%, like all four of these little sections colored in. So here you have two and then two. And here you have almost four and like a little sliver kind of thing. So check these out as you read, annotate, and do this section.